In the Beginning by Dr. Walt Brown. The flipbook is available at creationsciencecenter.org. We'll take a look at liquefaction during the compression event on page 212. While liquefaction operated during the flood phase, it acted massively once during the compression event at the end of the continental drift phase. See page 121. Visualize a deck of cards sliding across a table. Friction from the table slows the bottom card. That card, in turn, applies a decelerating force on the second card from the bottom. If no card slips, the entire deck, including the top card, will decelerate as a unit. But if a lubricant somehow built up between the two adjacent cards, cards above the lubricated water would slide over the decelerating cards. Likewise, each decelerating granite hydroplate acted on the bottom sedimentary layer riding on the hydroplate. Sedimentary layers from bottom to top acted in turn to decelerate the topmost layers. As water-saturated layer decelerated, it was severely compressed, similar to suddenly squeezing a wet sponge. Sediments forced into a denser packing arrangement released water. Sedimentary particles were crushed or broken, so their fragments filled the spaces between particles, releasing even more water. The freed water then forced up through the sediments caused massive liquefaction. As the sedimentary layers decelerated and compressed, they became more and more fluid. Eventually, some layers were so fluid that slippage occurred above them, as in our decks of cards. Below that level, extreme compression and liquefaction caused fossils to float up and collect at this watery level where sliding was taking place. A major slippage surface is called the Cambrian Precambrian boundary. Fossils are found exclusively above this interface. Therefore, evolutionists interpret the Precambrian as about 90% of all geological time, a vast period, they believe, before life evolved. A few feet above the global interface are found representatives of all animals and plant phyla. See the Cambrian explosion on page 20. This presents a huge problem for evolutionists. How and why did so much life evolve so fast? A phenomenon evolutionists call the Cambrian explosion. Again, evolutionists are unaware of global and massive liquefaction and mistakenly measure time by sedimentary layers and their fossils. In the Grand Canyon, the Cambrian Precambrian interface is almost flat. Horizontal surface exposed for 66 miles above the Colorado River. Layers above the Precambrian interface are generally horizontal, but layers below are tipped at large angles, and their tipped edges are beveled off horizontally. See figure 108. Figure 108. 400-foot cross-bedded sandstone, Cambrian, Precambrian. And notice the block. Grand Canyon cross-section. The tipped and beveled layers are part of the Precambrian. The horizontal beveled plane at the Precambrian interface is sometimes called the Great Unconformity. A similar but much smaller example of tipped and beveled layer is shown in the cross-bedding sandstone in figure 117. Beveling implies relative motion. Near the top of the Grand Canyon is a 400-foot thick layer of cross-bedded sandstone. The white circle indicates the location of the quartzite block, shown in figure 119. Okay, or figure 109, the quartzite block. Figure 109, transported block in the Grand Canyon. In the left figure, notice the large 5 to 10 ton block near the center and the shadows of the photographer Jim McDowell, my son-in-law, and two grandsons, Sean and Ryan McDowell. The right figure is an enlargement of the block with Ryan and Sean left to right. An article by a geologist, Professor Arthur V. Chadwick, brought this block to my attention in 1978. Later, we got to know each other when he visited my office. The block is a very hard material called quartzite. It was lifted, transported from right to left. The deposited and deposited on layers which at the time were soft mud. Other mud layers then blanketed the block. See the deformed layers below and above the block. Professor Chadwick correctly identified the lifting force, a very dense, rapidly flowing sand, mud, water slurry, which plucked the block off the lower quartzite layer upstream, far to the right of this picture. Part of that pink quartzite layer is seen in the first picture, lower right here. The easiest way to lift and transport such a heavy block is in a dense, liquefied, and therefore very buoyant sedimentary water mixture as is flowing at high velocity. This rapid transport, which was immediately above the Cambrian-Precambrian interface, occurred during the compression event. Below the sliding slurry, a sand layer decelerated and compressed first. The compression squeezed up water that lubricated the slide and heated the quartzite sand, so it became quartzite. Compression also tipped the layers up, causing them to be beveled by the overriding sliding layers. The camera is looking north, therefore the slurry slid from east to west, which is consistent with the direction of the American hydroplate slid away from the mid-Atlantic ridge. Evolutionary geologists who do not understand the physics and rapid continental drift that ended in the compression event explain the flat Cambrian-Precambrian interface as the result of hundreds of millions of years of erosion. For them, unimaginable time explains everything. Lazy and sloppy thinking. Figure 108 for a cross section of this region. The block is located there. Hikers should not attempt to reach this remote, rugged, off-trail location unless they are in excellent physical condition and have permission from the Grand Canyon's Backcountry Office. Wow. And let's take a look at the cross-bedding. What page are we at? 213. Cross-bedding sandstone. Yeah, right there. There's the cross-bedded sandstone. Wow. Oops. Okay. Let's go back. Okay, so we saw figure 108. Okay, and their tipped edges beveled off horizontally. Okay, layers above the Cambrian-Precambrian interface are generally horizontal, and layers below are tipped at large angles. Okay, we saw that. As slippage began during the compression event, layers below the slippage plane continued to compress to the point where they tipped. The sliding sedimentary block above the slippage plane beveled off the still soft tops of the tipped layers. Evolutionists have a different interpretation. They believe tipped Precambrian rocks are remnants of a former mountain range because mountains today often have steeply tipped layers. The tipped layers are horizontally beveled, so evolutionists say the top of the mountain must have eroded away. That would, of course, take a long time. Millions of years are also needed, so seas could flood the area because fossils of sea bottom life are found just above the Cambrian-Precambrian interface. Within overlapping layers, other fossils are found which require different environments, such as deserts or lagoons, so obviously even more time is needed. Unlimited time makes the nearly impossible seem possible if you don't think too much about the mechanisms. Cross-bedded sandstone. Sand layers have had the greatest water content because sand grains are somewhat rounded, leaving relatively large gaps for water between the particles. Therefore, sand layers were the most fluid during the massive liquefaction that accompanied the compression event. Deceleration forced the sand forward, displacing the water backward. Horizontally compressed sand layers would have slid, tipped, buckled, and beveled individual layers and blocks of layers, exactly what we see in cross-bedded sandstone. Liquefaction, plumes and mounds. I think we're going to stop. Let's see what's in these pictures. There's the plumes. There's the mounds. There's some technical stuff. Okay, yeah, we'll stop there. In the Beginning by Dr. Walt Brown. Get the flip book at creationsciencecenter.org.